Yeah. Okay. Let me share my screen. Okay. So we were talking about how Hermitian operators work in this formalism, right? And we said here that if it's Hermitian, if you can take the operator and put it onto the beta, right? And we're saying, hey, look, if alpha, the ket for alpha is a column vector like this, the ket for beta is a column vector like this, the bra for A is a star row vector, and the bra for B is a star row vector, right? So this is kind of B transpose star, right? Or sorry, B dagger, right? This is the dagger. And so if we were going to write this out, right? Let me get my yellow color again. If we were going to write this out, then it would be B transpose Q acting on A, right? Let me get to my part, that part of the notes. Give me a second here. For some reason, I didn't get that organized. Okay. 1 second. I picked up the wrong folder. Okay. Okay, this is not working out here. I am missing a folder. That's why I picked up the wrong one. Give me a second. Where is lecture 4? What is going on? I'll be right back, guys. I don't know what happened, but I cannot find my lecture 4. It is missing. That's very strange. This is lecture 4, lecture 5. Oh, wait. Maybe I just put it under here. Oh, yeah. Here it is. All right. Sorry about that. Okay. Okay. Right. All right. So if Hermitian, so this, if we write this out, right, this is what this side looks like. Now, if it's Hermitian, we know that it has to be equal to this other thing, which was Q beta alpha, right? And if we write that in matrix notation, this is going to be Q beta dagger, right? Oh, sorry, Q B. Let me erase that. It's too confusing. Remember, B is our matrix version of B, or vector version of B, of beta, I mean. And then A, right? Does this make sense? And so if we look at that, right, we see that this has got to be, so what ends up happening here is that Q, right, must equal Q dagger for it to be Hermitian. So this is the same as saying that this guy here, right? So this is how I'm going to write this out. Sorry, is going to be Q dagger B A. Remember, you have to switch them around, and so Q dagger has to be equal to Q for hermeticity. So you can check if you know the matrix form of an operator, right? If you know the matrix form of an operator, you can check that it's Hermitian. And you don't have to do this, this integral. Remember, this is really an integral. You have to do the integral. You can actually just see, is the Hermitian conjugate of the matrix equal to the matrix, right? So, for instance, remember the H that we were just dealing with in the previous lecture? We had this H, G, G, H with H and G real. Let's see if it's Hermitian. Well, what's H dagger? Well, H dagger is the transpose of H star. Okay, so the first thing we do is take the transpose, and that's just I'm flipping over the diagonal. So we have H, G, G, H, because the transpose seems to just be H, right? And then we have star. And because everything is real, if you put a star on everything, you just get the thing back, right? So you get H, G, G, H, and indeed, this is equal to H, and thus it is Hermitian. Yeah? Let's try another one. Let's try an operator T that is matrix representation is 1 minus I, 1 plus I, and 0. Okay? So what do you think? What's your guess? Is it Hermitian?
Yes.
Okay, Jackson says yes. Tyler's not sure. Okay, why don't you do these operations and see what happens.
If you're wanting, but
How's it going? What'd you find? Yes. Hermitian, yes? Yeah, it doesn't look Hermitian, does it? Certainly doesn't look symmetric. But if you put those two things together, the transpose and the star, you indeed get that it's equal to itself. So let's try it. So first we're going to take the transpose. So I have 1 plus I, 1 minus I, 0. And then I got to take the star. And that just gives me 1, 1 minus I, 1 plus I, 0. And indeed, this is T. Okay, Hermitian operator. All right, awesome. Okay, let's leave this chapter and move on to chapter 4. And chapter 4 is all about quantum mechanics in 3D. Because if you want to do things like the hydrogen atom, you got to do 3D, right? There's no two ways about it. There's no one-dimensional hydrogen atom model. Okay. All right. So this is chapter 4. QM in 3D. Now, chapter 2 was all about QM in 1D, right? So there's a lot of stuff that we did in chapter 2 that we'll be redoing in chapter 3 in 3D. I mean, not really, but it's very similar, right? So we started chapter 2 using the TISE, right? The TISE was the separable, the one of the equations we got from using separable solutions, right, to the TDSE, right, the time-dependent Schrodinger equation. And so now we've got to redo that work when we have 3 dimensions now, because we don't have just X now, we have X, Y, and Z, okay? And we will be solving the TDSE using separable solutions, but we'll have to do that a couple of times because we may use different coordinate systems, okay? So if we decide to use spherical coordinates, we've got to solve the TISE, the TDSE, we've got to do separable solutions in spherical coordinates, right? So we're going to be doing it, figuring out what the equations are with separable solutions in several different instances. Okay, so let's just start by writing down some things, how things are different in 3D. Okay, so let's see. First of all, in 3D, right, we have the regular old Schrodinger equation, the TDSE, doesn't look very different. Right, this is the TDSE. Remember the H operator, right? So I'm going to write down the H operator. This doesn't look different in this form, but the H operator is a little different because it doesn't just have the momentum in the x direction, right? It has the momentum in the x direction, y direction, and z direction if you're in Cartesian. Okay, so in 3D using Cartesian coordinates, Cartesian, the Hamiltonian looks like this. 1 over 2m, and actually the operator, I don't need the operator sign because I want to write it in terms of momentum first. So it's 1 over 2m, then it's the square of the momentum in the x direction plus the square of the momentum in the y direction plus the square of the momentum in the z direction. Okay, and plus, of course, in general, v of x, y, z, and t, right? In general, that's what that is, right? Now again, just like in chapter 2, we're going to restrict ourselves to v's that don't have t, okay? So we'll not have t, only x, y, z, or other coordinate systems, right? If we're in other coordinate systems, it might be v of r theta phi, right? Okay, so in other words, if that's spherical. All right, so if we look at that, so what does that mean? So we know that px is just h bar over I partial x, which I'm going to write as h over I partial this is, partial x like this, right? This is our notation we used in 371, just to keep from going nuts with too many partials, okay? All right, well, py, you can imagine, looks very similar to this, right? And pz is partial z, right? So this is what the operators look like, the momentum operators look like. And so if we write down the Hamiltonian in terms, so now the Hamiltonian operator, we substitute these in for, right? What do we get? Well, it's h bar, it's minus h bar squared for one thing. And then it's partial squared x, right? Plus partial squared y plus partial squared z, right? Where that partial squared z, etc., is partial squared. Sorry, partial squared z is partial squared partial z squared, right? It's a shorthand, right? And then plus rv. Right? Well, this may look familiar, this thing here. It is actually del squared. And this is cool because if we know it's del squared, then we know what del squared is in all the other coordinate systems, right? So we immediately know how to write down the Hamiltonian operator in any other coordinate system we like. Okay, so this means that the Schrodinger equation now is I h bar partial psi partial t is equal to minus h bar squared over 2m del squared psi plus v psi, right? Yeah. And of course, remember that del squared is the Laplacian. And I'll write it out here just to be really formal about it. D squared dx squared plus d squared dy squared plus d squared dz squared. That's Laplacian, okay? Okay. Now, if we wanted to look at something like what's the probability of finding the particle, well, just like before, it's going to be psi star psi. And if you want to find a particle in a particular infinitesimal volume, you have to do an integral. Okay. So can I go to a new layer? Wait for a second. Good? Okay. Okay. So if we want to calculate the probability of finding particle in volume, well, sorry, in infinitesimal volume, I cannot spell. I have no idea if there's two S's in that or not. I think there are two S's. You can correct me if I'm wrong. In infinitesimal volume, and that would be given by D3R, this is the notation we use, which is dx, dy, dz, right? And of course, if this was in a different coordinate system, right, D3R would mean a different thing, right? So for instance, in spherical, so this is Cartesian, and d3r in spherical, d3r in spherical is r squared sine theta d r d theta d phi, right? So it looks a little different in different coordinate systems, the infinitesimal volume element. But it's what we just use this notation d3r, right? The idea is it's a little tiny box, right? Okay, little tiny volume element. All right. So in finding the particle in that little infinitesimal volume element is, psi, and sometimes we write like this of RNT. That's just a shorthand for all three of the coordinates, right? Whether you're in spherical or, um, you know, um, Cartesian or cylindrical polar or whatever, right? This R with a vector sign over it means it's a shorthand for all three dimensions. Okay, it doesn't mean you're in a specific coordinate system. So it's this d squared and then d3r. Okay, right? Just like before, but now we're in 3D, right? Okay. And of course the normalization, right, is psi of r t squared d3r. Because remember, when we normalize, right, this is normalization. Right, when we normalize, we have to integrate over all space. And in this case, all space is literally all space with all three dimensions. Okay? All right. Okay, so if we, again, we're going to take V not to have any time dependence. If we do that, then in general, you're going to have an infinite number. So we take, let's see, so take V to not have time dependence. Again, just explicitly stating it. Then, so it's going to be V only of XYZ, or V of R, theta, phi, or we could write just V of R like this. It's a shorthand for any of those, right? Then we have a set. Oh, why did I write these? I don't know. Set of solutions to the TISE that are complete, right? Again, this is completely analogous to the 1D case, right? That are complete. So in other words, you have, these guys, psi n of r, again, this is the shorthand for 3D, is equal to little psi n of r, and then e to the minus I e n t over h bar. So the time dependence really does not change. It's just like 1D, nothing changed there. It's this thing that now is a function of 3D, of three coordinates, right? Okay. And psi, of course, little psi n is the solution to the TDSE, which looks like this, right? We just wrote it down, sort of. H bar squared over 2m, del squared, little psi, plus v, little psi equals e
Wait,
psi.
I thought little psi was the time independent Schrodinger's equation.
Yeah,
Well, I thought you said the little psi is that, or are you setting them equal to each other?
setting what equal to each other? What do you mean?
Wait, um, what is are you now putting time independent Schrodinger's equation in as that? So
This is the time independent. Oh, why did I wrote TDSE? I'm sorry. Is that what you're confused about?
yes,
Yeah.
yes, I am.
TISE. Sorry, TISE, which is this, right? These guys are solutions to TISE, right? Okay, sorry about that. Yeah. So this is the TISE, the usual thing. So the time dependence does not change at all, right? And of course, our general solution for a particle is the linear combination of states with some coefficients. So this is no different than you've seen in 1D. It's just that we have more than one coordinate, right? We have x, y, z, r theta phi, whatever. Okay, so nothing's different. Now, typically, right, we're going to be dealing with at least, I'm trying to think, are we only going to deal with, we might deal with 2 or 3 potentials that are not just functions of the distance from the origin, but a lot of potentials that we're interested in, for instance, the potential energy function for the hydrogen atom is just a function of the distance from the center, right, of the atom, right? So if you can imagine the electric potential due to the proton is just 1 over, it goes as 1 over r, where r is the distance, not the vector, right? The magnitude of r, 1 over the distance to the electron. So a lot of times v is not going to have any dependence on any other variable but the magnitude of r. Okay, so I'm going to just look at that case first, and because it's so important to our most important solution in 3D, which is the hydrogen atom. So that we're going to start with spherical coordinates, which is unusual, right? We usually don't start with the spherical coordinates, but we are going to start with spherical coordinates. All right, so I'm going to need a new layer, so let me know when I can do that. Okay.
One question.
Yeah.
The value of Cn in this, is that the value we get with normalization?
No, that value with so remember that normalization, you stick just a thing in there like a,
Okay.
right? And then you solve for a and you get some factor that you put in front of all the size, right?
All right.
For instance, in the infinite square well 1D case, it's the square root of 2 over a that you stick in front of every one of the size. But the CNs are a measure of how much of each of the different size are mixed into your big state, big psi. Right?
So it's a constant value for every n value?
Yeah, it could be different for every n. Most of the time it is, right? Because right, it's unusual to have it be exactly equal for all sides. So for instance, you could have, you could have Cn be super big for one size. So let's say C1 is really, really big, right? And remember the square of all those CNs have to add up to 1. And then you could have, let's say, one other state that takes up the rest, right? Because the square of the CNs have to add up to 1. So right, you can't just make them as big as you like. But they're telling you how much of each of the little psi n's are used to mix in, to get your final state, that are mixed in to get your final state.
Okay.
Does that make sense?
Yes.
Okay, we've seen that a bunch of times in on chapter 2. Okay, new layer. Okay. All right. So let's stick with spherical coordinates. I'm going to change color again. So spherical coordinates. Spherical coordinates. Okay. So that's r theta phi, right? Where theta is the angle that comes down off the z-axis. Okay. And this is for cases, and we're going to deal with cases where v is only a function of the distance r. That is not a vector, that is just the distance, okay? Right, where r is equal to, you know, square root of x squared plus y squared plus z squared, right? The magnitude of r, okay? Okay, so we're going to deal with those cases only, and we're going to look for separable solutions, right? First, we have to actually write down the TISE, because it's kind of nasty in spherical coordinates, right? And then we're going to look for separable solutions. So let's just deal with the fact that the TISE, and I'm going to put here in red. So TISE looks like this in all coordinates. Right? So that's the TISE in every single coordinate. And now we have to find we have to deal with this, right? So in every coordinate system, this will be different. So in Cartesian, we already saw that del squared, right? So in Cartesian, del squared was partial x squared plus partial squared partial y squared plus partial squared partial z squared, right? Okay, but in spherical, it is not that. Okay, I'm gonna get another color. So in spherical, okay, del squared. We have del squared is equal to this big mess, 1 over r squared, partial r, remember that's code for partial r, okay, of r squared partial r plus 1 over r squared sine theta, and then partial theta, because that's code for partial theta, sine theta d theta, again, that's code for partial theta, plus, it gets worse, 1 over r squared sine squared theta, partial squared phi. And again, that's code for partial squared partial phi squared, right? Okay, so big ugly thing. Big ugly awful thing. Okay, so now when we substitute into the TISE, we get the, you know, kind of nastiness here. So now the TISE in spherical is this ugly thing, minus h bar squared over 2m. And then I have a big bracket here. And then I have 1 over r squared and partial r, and then r squared. And actually, I'm gonna not use my shorthand for this one. I think it's better just to, because it's gonna be messy enough. So partial, I mean, that shorthand is not as messy, but it's not as clear either. So partial psi, partial r, okay, plus 1 over r squared sine theta, partial theta of sine theta, partial psi, partial theta, and then plus 1 over r squared sine squared theta, and then partial squared psi partial phi squared. Okay, all that plus v psi equals e psi. So there's the TISE in spherical coordinates, right? Not the prettiest thing in the whole universe. And we're going to look for solutions that are separable, since we've done that before, right? So we've done it before in 1D. And I don't remember if we've ever done this in any other class that I've been with you guys in. You can remind me if we did or not. I think maybe we did in 371. I can't remember. Where we separated some equation in 3D in spherical coordinates. Anyone remember that? No, I don't think we did. Vaguely remember that in some class. Okay. All right. So we're going to look for separable solutions. And that means psi of r theta phi equals big R of r. It's only a function of r. And we're going to use a function like this. It's called y. You're going to see these are the spherical harmonics, but right now just think of it as a function of only theta and phi. I'm sorry. I don't know why it rings on my computer. Okay. Okay, so that is what we're going to look for. So we're not separating into 3 different functions yet. We're actually going to do this in steps. So the first thing is the r, so separating into a function that's only a function of the distance r, right? And then times a function that's only a function of the angles theta and phi. Okay, so let's do it. We're gonna substitute in to the TISE. All right. So let's just take a look at what happens to the derivatives. Okay. So right here, this derivative here, right? This is only going to act on the r portion, right? And this y theta phi is going to come out. This here is only going to act on the, and so also this derivative will only act on the r derivative, right? This derivative here will only act on the y theta phi, and the r functions can come out. So this derivative as well. Of course, this derivative will only act on the phi, on the y, and the r won't care. So let's put that in. All right. So we have minus h bar squared over 2m. And we're going to change it whenever we can, right? We're going to change our derivatives to regular derivatives, because as soon as they only are acting on a function of only one variable, so if you're acting your r derivative on the big function r, you don't need it to be a partial derivative anymore, right? It could be a total derivative, or an ordinary derivative, I mean. Okay, so we have 1 over r squared, and then we have our y function because it's just going to pull out of all the derivatives. And then we have d dr, because this is no longer a partial because there's only r squared in here and the big R. And we have r squared and then d big R dr. Okay. And then on this side over here, the next term, we have 1 over r squared sine of theta. And then we've got our r. I'm going to pull it out over here because it didn't need to go. It can pull right out of those derivatives, and the derivatives become ordinary. Oh, actually, no, sorry. Got to be careful here because y is a function of both theta and phi, so they don't become ordinary in this case. So we're going to do partial theta, and then sine theta, and then partial y, partial theta, and then plus 1 over r squared sine squared theta, and that's going to have now the r on the outside again, and then partial squared y, partial phi squared, and then plus v psi, v ry. Psi is ry, right? Ry equals ERY, right? Okay, next step is always dividing by ry, right? So we're going to divide everything by ry. So over here, the y will cancel, and we'll get a 1 over r term. Over here, the r will cancel, and we'll get a 1 over 1 over y. And here, the r will cancel, and we'll get a 1 over y again. Okay, so let's do it. So 1 minus h bar squared over 2m. And we're going to get a 1 over r squared d dr r squared dr, and then plus 1 over y times 1 over r squared sine theta partial theta sine of theta partial y partial theta plus 1 over y again, 1 over r squared sine squared theta, and then partial squared y, partial phi squared, plus v equals e, right? Because we divided out those ry everywhere. Yeah? Everybody following? I know it's messy. Okay. All right, now I'm trying to think what we want to do. Right. I want to get rid of these constants everywhere, so I'm going to pull them over onto this, onto the E and V. So for instance, I'm just going to rewrite this a little bit. So these constants are going to be pulled onto the E and the V because I'm tired of them in this big bracket. I'm actually also going to multiply everywhere by little r squared, because if you notice there's a little r squared here, there's a little r squared here, and there's a little r squared here, so I can multiply everybody by r squared and just move it up to the top instead of having it on the bottom. Okay, that's okay with you. And I'm kind of trying to also group everything that depends on r over on, one in one sort of area, and then everything that depends on phi and theta over on the other area. Okay. All right, so that's what I'm going to do. All right, so here we go. We're going to have 1 over r. The r squared's gone because I'm going to pull it up over here. I'm going to multiply everybody by r squared. Okay. The h minus h bar squared and stuff is also gone because I'm multiplying everybody by minus 2m over h bar squared. Okay, so now I have 1 over r ddr of r squared dr. Okay, and over here, I have y's and theta, so I'm just gonna be like, I don't want you right now. I want to move everything over that has r's in it. Okay, so what do I have? I have minus 2m r squared, right? Because I put an r squared on top of everybody, right? I multiplied through by r squared. And the 2m is on the top now over h bar squared. And then I have v, which is only a function of r minus e. So just a little algebra skip steps here, right? So I multiplied everybody by minus 2m over h bar. I multiplied everybody by r squared. And I pulled the e over. Okay? All right, so now look, this is all a function of r. Yeah.
Doesn't the minus h bar squared over 2m act on everything though? So it's not going to be multiplied to the second term.
What now?
The minus h bar squared over 2n, that's not going to act on just the first term. It's acting on every term, so you wouldn't have it on the I don't know. I'm lost.
Okay, so notice the big bracket here, right?
Yep.
See where that is?
Yep.
It doesn't act here. It's not here and here.
Yeah, right. So, oh, so we're just not done yet.
No, we're not done yet.
Okay, yeah, okay,
Yeah,
gotcha.
yeah, not done yet, not done yet. No. Okay, so now I'm going to have all the theta terms and phi terms because now I must want them over by themselves, right? So I have now plus 1 over y. Okay, and then I have this big thing, 1 over sine theta, partial theta, sine theta, partial y, partial theta, and then plus 1 over sine squared theta, partial squared y, partial phi squared. Okay, and that whole thing equals 0, right? Yep. Okay, so notice here we have this term here, I'm going to call that term 1, and this term here, term 2, that 1 only depends on r, and 2 only depends on, can't write today. On theta and phi, okay? So again, it's one of those things where hopefully you're familiar with this argument that if I change something over here, if I change r by a little bit over here, nothing changes over here, and therefore this equation will not hold, right? Anymore. So if I change r by a little bit here, or even a lot, nothing changes over here, and the equation is no longer true. Same thing here. If I change either theta or phi by some amount, this doesn't change, and so this thing cannot hold. So they both must be equal to a constant, and in fact, one is equal to the positive. Like if this is 2, this has to be minus 2, right? So if term 1 is 2, this has to be, no, term 2 has to be minus 2 for this to work. Yeah? Are you good with that? Yeah. All right, I'm going on to another layer. Yes? Okay. All right. So now this means that I can set them both equal to a constant, and one of them is the negative of the other, right? So this is what I'm going to do. I'm going to do 1 over r, and then ddr of r squared dr minus 2mr squared over h bar squared, and then v of r minus e. That I'm going to set that equal to a constant that looks like this, L plus 1. Now, why didn't I just send it to something like, 3 or something? Well, yeah, I could have, but I'm going to put it into a form that is meaningful for later, okay? All right, so we're going to say, okay, we have, so we have one constant. Now we know that the other equation has to be equal to the negative of this constant. So we're going to say 1 over y, 1 over sine theta, partial theta, partial y, partial theta, plus 1 over sine theta, partial squared y, partial phi squared. And this is going to be equal to the negative of that constant, right? Same constant, negative of the constant. Okay, so we have two equations, don't we? We have one equation for r that only has r's. That's excellent. It's a complicated equation, and it will not be easy to solve in general. And we have another equation for y. And I want you to notice something, there is no V, right, in the y equation. Right? There's no potential or the energy of the particle. That doesn't come into that as well, right? So neither of those has both either the potential energy or the total energy of the particle in it, right? So I'm sorry, the y equation doesn't have the potential energy or the total energy in it. So it does not, that y equation does not depend at all on the particular system that you're studying. Okay, except that we couldn't make this separable solution if V itself wasn't only dependent on R. So if V was dependent on theta and phi, then we couldn't have done this at all. So you can just throw that out the window, right? So in the case though, where V only depends on R, the equation for Y doesn't care what system it is, right? It doesn't care because V tells you what system it is. Is it a hydrogen atom? Is it a particle in a spherical box, right? What is it? Is it a 3D harmonic oscillator, like spherical harmonic oscillator? The y equation does not care. Okay, so we can solve the y equation and it'll be the solution for every single V of R, right? Which is great. All right, which just leaves us with the horrible R equation to solve for every different V that we want to solve it for. So again, not fun, but at least we don't have to solve the y equation for every single one too. Okay, so we can solve the y equation. So let's do it. Okay, so let's just rewrite this y equation a little differently. So we're going to solve the y equation. I'll do it in a different color here. So solve y equation. Okay, so first we're going to write it a little differently. I'm going to multiply everybody by sign, and I'm going to multiply everybody by y. Okay, so the y is going to cancel out here. The sign is not going to be on the, oh, sorry, I'm going to multiply everybody by sine squared. I meant, never mind. So y and sine squared. So I'm going to multiply by y and sine squared. Okay. All right, so when I do that, what do I get? I get sine theta, partial theta, sine theta, partial y, partial theta, okay? And then plus sine theta. Oh, I messed this up. This is sine squared theta. Oops, sorry about that. Okay, plus partial squared y, partial phi squared. And on this side, I get minus L plus 1, y, sine squared theta. Okay? Okay, so again, we have a function y. Remember, y is a function of theta and phi, right? We want to make it now a function we want to write that function as the multiplication of two functions that only depend on either theta or phi. So in other words, theta of theta and capital phi of phi. Okay, this is a separable solution. Okay, and there's literally kind of no reason not to do that at this point, right? There's no reason to think that your solution will not be able to do this because V only depends on R, and if V depended on theta and phi, then one, we wouldn't be able to do this at all, but then you'd also be doubting yourself as to whether you could ever have a separable solution even for the angles, right? So, all right. So, but we're just going to go with this and see what we get. So again, substitute in. The partial derivatives are going to become ordinary derivatives. The y here, this part here, the theta derivatives will only act on this guy, and the phi derivatives will only act on this guy. Okay? All right. So let's see what happens. So we're going to put sine theta. And because these are theta derivatives, the phi function can just come right out. and I get the ordinary derivative of sine theta dy d theta, okay, plus now the theta function comes out of this derivative, and I get the ordinary second derivative of the phi function with respect to phi. And on the other side, of course, I get minus L plus 1 theta function, phi function, sine squared theta. All right. So again, the next
Wait.
step always, oh yeah, go ahead.
Going back, wouldn't it be d capital
Oh yeah.
theta over instead of dy?
Yeah, you're always catching my typos. Thank you very much. Yeah, capital theta. Good. I appreciate it. Okay. Okay. So now we're gonna, as we always do, we divide through by theta phi everywhere. Okay. So on this case, on this side, we're gonna have theta phi over theta phi. You're just gonna get 1. Over here, you're gonna get 1 over phi, and over here, you're gonna get 1 over theta. So here, let's write it again: sine theta over capital theta d little theta sine little theta d capital theta d little theta, okay, plus 1 over capital phi d squared capital phi d phi squared equals minus L plus 1 and sine squared theta. Okay. Oh yeah, Chromebook. Sorry. All right. Okay. So again, we have a very similar situation, right? We have 2 pieces, and you can see that one piece here, this is a piece here that only depends on theta. This here and this here together only depend on theta. This here only depends on phi. And again, we have that similar situation where we have 2 pieces that don't really interact, right? So they have to be equal to a constant. So the way I'm going to write it, and let me just make sure I'm writing it right. Yeah. So I'm going to write everything on one side one more time here. So let's just write everything on one side. So I'm going to do all the theta stuff over here. Okay. And then plus L plus 1 sine squared theta. Okay, so that's all the theta stuff. And then on the phi stuff, of course, is 1 over capital phi d squared phi, capital Phi, I mean, d phi squared, okay? And that's all equal to 0. Again, same argument, right? This term here better be equal, if this is equal to 2, this one better be equal to minus 2, right? Otherwise, this equation will not hold because there's no phi's over here and there's no thetas over here, okay? All right, so let's do that. Let's set d squared, 1 over phi, so it's going to give us 2 equations. 1 over phi, d squared phi, d phi squared, we'll have that be the minus m squared. And we'll let the sine theta over big theta d theta sine theta d big theta d little theta plus L plus 1 sine squared theta equal m squared. Okay. Okay. Now we can solve one of these right away. I actually can solve both of them right away, but one of them is a little bit more of a pain. This one right here is relatively easy to solve. Okay. So let's look at this equation. I'm gonna need a new layer, so I'm gonna wait for you there a little bit. You good, Jackson? No, not quite. Okay.
On days like today, I feel my handwriting so much.
Yeah, right. I know. Jackson, good? Yeah, okay. Let's go to a new layer. All right, so again, I'm gonna write the equation down. So we have the two equations we are working with are the 1/5 d squared phi d phi squared is equal to minus m squared. And I'll do that one in a different color. And the 1/big theta sine theta d theta of sine theta d big theta d theta plus L plus 1 sine squared theta equals m squared. Okay, these are the two equations we're dealing with now. So let's solve the blue one. Okay, so what can we do? Well, it's not an easy, not a difficult one to solve. This one should look a little familiar. So let's write it in a different form. Okay, this form is the same form as the, Newton's second law for a harmonic oscillator, right? D squared x dt squared equals minus kx, right? It's the same form as the infinite square well Schrodinger equation. D squared psi dx squared equals minus square root of 2, minus 2me over h bar squared psi. It's a very similar form. And in these kind of equations, what we always try is an exponential. Okay, so we're going to try an exponential. Okay, e to the lambda phi. Yeah? Okay, so let's try it. So the first derivative of e to the lambda phi is lambda e to the lambda phi, and the second derivative is lambda squared e to the lambda phi. So we get lambda squared e to the lambda phi is equal to minus m squared e to the lambda phi. And of course, these guys cancel out, and you can solve for what lambda squared has to be, right? So lambda squared is minus m squared, and therefore lambda is plus or minus m. Yeah? Okay. Well, in fact, we're going to incorporate the minus sign into the m. And so I'm just going to write e that our solution for big phi is e to the I m phi. Okay. And we now have to think about what the boundary conditions might be for this guy. So remember, this is the azimuthal angle, right? This is the angle that goes around the xy plane. Yeah? So it goes around the xy plane. And we would expect that our big function phi, given that it really doesn't depend on anything except for this constant m, would be periodic, meaning that if you have a value at phi equals 20, when you come around again to phi equals 20, big phi should be the same, right? right? So if big phi is a certain value at theta equal, or sorry, at phi equals 20, it should have the same as it comes around, right? So if you add 2 pi to that 20, sorry, 360 to that 20, right? You should come back to the same value of big phi. I think that makes sense, right? Why would we expect it any different? There are solutions to the Schrodinger equation that are not, this is not the case for, but those are for when you have V, the potential energy function also be a function of phi, which we don't have. Okay. All right, so our boundary conditions are that big phi of some phi should be the same if I add 2 pi to it. But that's only true if m is an integer, right? M has to be an integer for that to work. Yeah? So m can be 0 plus or minus 1 plus or minus 2 dot dot dot. Okay? So not too hard. So we now have a solution for big phi. With okay. All right. What about the other equation? Right? What about our equation for big theta? Right? That's not as easy to solve, and I'm not actually going to go through the solution. But I will tell you what the solution is. I'm not going to actually solve it for you, but there are lots of places you can go look this up. So the solution for phi of theta is some constant, which we'll get to, some constant a, times the associated Legendre functions PLM as a function of cosine theta. Okay, so these guys are here, the associated Legendre functions. Okay, and you get the associated Legendre functions from the Legendre polynomials. Okay, so from this function, so we have p. Well, let's go back to our. Okay. So we have PLM, the associated functions of x. So whatever is in this spot, right? So this one's a cosine, but you can put anything in this spot. Is defined as 1 minus x squared to the absolute value of m over 2. The mth derivative, so you have to put the absolute value on the m here as well. Mth derivative of the Legendre polynomials. And this is the Legendre polynomial. Okay, so for instance, what are the Legendre polynomials? Well, let's look at P0. So when L is 0, it's just 1. When it's 1, it's just x. P2 is 1 over 2, 3x squared minus 1, okay, etc. So you can just go look those up, right? These are things you just look up. And of course, you can also look up the associated Legendre functions. You don't have to do all this to get it, but just writing that down for you. Okay. And we can take a look at one of them. So for instance, let's look at the associated functions And let's use this formula just to get one of them, okay? So I would like to get P 0, 0, right? That's L equals 0 and M equals 0. Okay, so from this formula, I know I have to take 1 minus x squared, and M is 0, so to the 0, right, which is just 1. And then the 0th derivative, okay, which is just the function itself, right, of P0. All right, well, that just gives us 1, right, doesn't it? Because the 0th derivative just gives you the function back, and this is just 1, right? Okay, so that's P00. Okay, what about P11? No. P11, okay, so let's see if we can get that. And we're going to stick with x, but we'll put cosine theta in there in a minute. Okay, so P11, we need to, this is P1. We need to take 1 minus x squared to the 1, right? Cool. And then dx, the first derivative, so I don't even need the 1 on there, so I'll get rid of that. There we go. Of x. So dx, right? Okay. So, because it's the first derivative here, and this is P1. Okay. So this is just going to be 1 minus x squared. Oh, I forgot the m. This is the 1/2 to the 1/2 here. Sorry about that. To the 1/2. Yeah. Okay. So this is P11 of x, but we need to put a cosine in for x now. So P11 of cosine of theta is 1 minus cosine squared theta to the 1/2. Of course, 1 minus cosine squared theta is sine squared theta, and to the 1/2 is sine theta. Right? Okay, anyway, that's enough of that. We do not have to use these formulas to derive this because you can look it up anywhere. Okay, if you want to know what the Legendre polynomial is, you can look it up. You want to know what the associated Legendre function is, say you want P23 or something, right? You just go look that up. You don't use the formula in general. You don't have to do that. But the cool thing about this is what they look like. Okay, so if we look at, say, the magnitude of these P00 of theta, okay, you'll look like something like, spherical, something spherical like this. If you look at, say, what this is, P10 of theta, it looks like this. Oh, no, wrong axis, sorry. Z-axis. Right? Let's look at P21. Looks like this. What does this remind you of?
Orbitals?
Mm-hmm. Exactly. Remember, this thing, these Legendre polynomials are what this theta of theta is. And this is part of a solution to a spherical coordinate Schrodinger equation for any V that only depends on R. So it certainly will be the solution for the hydrogen atom, right? So that's what these look like. And we're a minute over class, and we'll come back to this. And we haven't even started at all on the R equation because we'll be doing that for different systems because that does depend on V. All right, gang. Your test will be ready by midnight tonight.
Hey, Dr. Shank.
Yeah.
Zoe said she sent you something. This is like not relative to class at all, but like she told me she sent you something
Uh-huh.
and wanted me to ask if you got it.
Oh, did she send it to school? Yeah, right?
Possibly.
Yeah, I'm pretty sure she did. Yeah, I haven't picked up anything from the mailbox yet in a while.
I
Okay.
gotta go.
Yeah, tell her
Bye.
I'll look for it.
All right. Sounds good.
Okay, bye.
Bye.